You ever stare at a graph, trying to pull a clear signal out of a noisy mess? Well, what if the most important information isn't in the data points themselves, but kind of hidden between them? Today, we're diving into a really powerful technique that lets you see what your standard spectrum is trying to hide. It's called derivative spectroscopy. And for anyone in pharmaceutical analysis, this is a tool you're definitely going to want to know about.
So picture this. You're in the lab, maybe running QC on a new drug. You prep your sample, you run it through the spectrophotometer, and what you get back well, it looks like garbage. It's this lumpy, sloping line where you know a sharp, clear peak is supposed to be. This is the analyst's dilemma, right? Your target is in there, but it's completely hiding in plain sight, just buried under a mountain of interference.
Okay, take a look at this. This is exactly what I'm talking about. See that nice, clean peak? That's the dream. But in reality, you get the spectrum on the right. Our signal is totally swamped by this huge, broad peak from something else in the sample. Like a tablet excipient or maybe some gunk in a syrup. If you tried to measure that peak height, you'd be guessing. And in our world, a guess is as good as a fail. You're flying blind. So what do? Just toss the sample and start over? Nah, there's a much smarter way. We're going to apply a mathematical lens to bring that blurry data into sharp focus. It's almost like putting on a pair of X-ray glasses that can see right through all that noise. And this elegant solution, this lens, is what we call derivative spectroscopy. So what is it really? In simple terms, instead of just looking at the absorbance value, let's call that the height of a mountain, we're going to look at the slope at every single point. We care less about how high the mountain is and more about how steep the path is. By focusing on that rate of change, we can totally zero in on the sharp, interesting features, our peaks, and pretty much ignore all the broad, gently sloping hills of background interference. Let's see what that actually looks like. Right. This is ground zero, the view we all know from Spectroscopy 101. It's our standard, zero-order spectrum, just a simple plot of absorbance for wavelength. And look, in a perfect world with a pure sample, this is all you'd ever need. But we know the real world is messy. And that's where this standard view starts to let us down. Now this is where the magic starts. We've taken the first derivative. We're not plotting absorbance anymore. We're plotting its slope. And check this out. At the very top of that original peak, the lambda max, the curve is flat for just a split second. Its slope is 0. And that's why on our new graph, we get this beautiful 0 crossing point. It's like a secret signpost in the data, pointing and saying, hey, the peak was right here. And if we push it one step further, we get this. The second derivative. Now we're plotting the curvature of that original peak. And right at that lambda max, where the curve has its sharpest downward bend, we get this incredibly sharp, distinct, inverted trough. We've just transformed a fuzzy, broad blob into a crystal clear signal that pinpoints the original peak's location with amazing precision. So, now that we get the basic idea, let's talk about what this can actually do for us in the lab. I like to think of derivative spectroscopy as giving us a couple of analytical superpowers. And the first one, well, it's pretty much X-ray vision for your data. I mean, just look at this. On the left, in the normal spectrum, you see what looks like a single perfect peak. You'd bet your career it's just one compound and you'd move on. But then you apply the fourth derivative and bam, 2 totally distinct peaks pop right out, clear as day. This is an absolute game changer when you're analyzing, say, a multi-component drug where the signals are practically sitting on top of each other. So how does this work? It's all about sharpening. It's like taking a slightly blurry photo and hitting the sharpen button in your photo editor. All the hidden details just pop into focus. Mathematically, what's happening is it's narrowing the effective width of the spectral bands, which lets them stand out from the background and, more importantly, from each other. You get a much, much truer picture of what's really in your sample. Okay, but X-ray vision is just the start. The second superpower is, you could argue, even more useful. It's the ability to make things disappear. And not just anything. It makes all that junk, that messy background interference that's ruining your analysis, practically invisible. This quote from an Agilent note really just hits the nail on the head. The whole process acts like a filter. It separates the sharp, interesting signals, that's your analyte, from the broad, boring background noise. Because we're focused on slope and curvature, those broad signals with their gentle slopes just get squashed down, while the sharp signals with their steep slopes get amplified. It's such a simple but powerful concept. Here's a perfect example of the problem. On the left, a nice, clean signal. On the right, that same signal is being totally washed out by light scattering from little particles in the sample. Think about insoluble stuff in a tablet formulation. It's like trying to have a conversation in the middle of a loud party. You just can't hear the signal over all that background noise. So what happens when we use this technique to kind of quiet the room? Well, in that example, the error in the standard measurement was over 9%. I mean, that's totally unacceptable. But by taking just the first derivative, that error plummets to just negative 1.1%. That's the difference between a failed batch and a product that's good to go. A fantastic real-world example is trying to measure caffeine in a soft drink. All the sugars and the colorants, they create this huge, broad background signal that completely buries the tiny caffeine peak. But with the second derivative, you can make that entire matrix effectively vanish, letting you measure that sharp little caffeine peak with pinpoint accuracy. It's a perfect illustration of seeing the signal through the noise.
All right, I know what you might be thinking. This sounds a little too good to be true, right? Like some kind of magic wand for every analytical problem. And you'd be right to be a little skeptical. Because like any powerful tool, derivative spectroscopy has its limits, and it's really important to understand the trade-offs.
So here's the big trade-off. While it's amazing at getting rid of broad background, it can actually amplify high-frequency noise. Think of it like this. The very property that makes it great at amplifying our sharp analyte signal also makes it great at amplifying sharp, random instrument noise. So as you go to higher and higher derivative orders to resolve your peaks, you're also turning up the volume on the static. It's a balancing act. So after all that, what's the big takeaway? For me, it's that derivative spectroscopy isn't just another button to click in your software. It's a fundamentally different way of looking at your data. It's a good reminder that there's always more to the story if you're just willing to look at it from a slightly different angle. And what's crazy is that this idea has been around since the 1950s. But back then, they just didn't have the tech to do it easily. It wasn't until microcomputers showed up in labs in the 70s that we could finally unlock its true potential. It's a great example of an old, powerful idea just waiting for the right technology to come along. So when should you reach for this tool in your analytical toolbox? Well, ask yourself these questions. Is my peak buried under another broader peak? Am I fighting with a messy, drifting baseline or scattering? Do I need to find a tiny amount of my analyte in a really complex sample? Or, hey, do I just need a reliable answer faster than an HPLC run can give me? If the answer to any of those is yes, derivative spectroscopy might just be your hero. At the end of the day, this whole technique is a powerful reminder that sometimes the answers we're looking for are right there, hiding in plain sight. We just need the right perspective, the right lens to see them. So the next time you're faced with a messy, confusing set of data in any field, don't be afraid to look at it differently. Ask yourself, what is the change in the data telling me? You might be amazed by the story you uncover.